Mathematics is not just numbers on a page, it's the language of the universe. And one of its most powerful ideas is the ability to describe how things change over time. In this lesson, we're going to explore a concept that governs everything from population dynamics to radioactive decay, from bacteria multiplying in a petri dish to the cooling of a hot cup of coffee. Welcome to Growth and Decay, where calculus reveals the hidden rules behind nature's most fundamental processes. At the heart of this topic lies a simple yet profound question. How does a quantity evolve over time when its rate of change depends on its current state? This actually leads us to an equation, and you may be familiar with this growth and decay equation of y equals c e to the kt. Now, if you are familiar with this, then you will know that c is the initial amount, t is the amount of time, y is just the amount present at any given time, and k is the constant of proportionality, or how rapidly is it expanding or is it declining over any given period of time. By the end of this lesson, you're going to see how we can use derivatives to unlock the secrets of this exponential growth and decay that's going to allow us to model everything from finance to physics, biology to engineering. So let's start by taking a look at the derivative of y equals c e to the kt. Okay, so we want to take the derivative of y equals c e to the kt. C and k are constant. That just means that these are numbers. So c is just a number and k is just a number. So remember, and t is our variable. So remember, if we have a constant raised to a power, the Euler's number raised to some power times a constant, we're going to go ahead and we're going to set CE to the KT. We're going to set KT as our U value. So we're going to have CE, it's going to be e to the power of U. So remembering back a few lessons, if I want to take the derivative of something that's e raised to the power of U, and in this case, we are setting U equal to KT. U is equal to KT. So if I want to know the derivative of that, remember the derivative of e to the power of anything is just equal to e raised to the power times the derivative of the power that it is raised to. So we have a constant times e raised to a power. So if we want to take the derivative of that, our dy over our dt, because that's the variable that we're looking for, is simply going to be our EU value, which in this case is c e raised to the power of kt times the derivative of our what we've set as our u, which is the power. Now, the derivative of kt, remembering that k is just a number and t is a variable, so we're going to use the product rule. So this is going to be equal to our derivative of our number k, so derivative of a constant is 0, times t, so derivative of the first times the second, plus the first, which is our number k, times the derivative of the second. The derivative of t is just 1. So our derivative of kt is just going to be k. Filling that back into this, where we have e to the u times the derivative of u, we end up with ce to the power of kt times k. So that is our derivative of ce to the power of kt. So in many sciences, certain quantities grow and decay at a rate that's proportional to their size. So if we have y equal to f at some time t, and the rate of change is proportional to size, then we know that the derivative dy over dt, which we just saw, is equal to that k value times the y value. This equation is called the law of natural growth if k is greater than 0, and the law of natural decay if k is less than 0. To solve this equation, we have to think of a function whose derivative is a constant multiple of itself. This function is exponential. So we are going to use f at t is equal to c e to the kt. And we need to set up a little bit so that we know what we're talking about here. So y is the amount present at any time t. So y is the amount present of whatever it is we're working with at any time t. Okay. C is just the initial amount. Of whatever it is, the bacteria, the radioactive particle, whatever it happens to be. T is the time. And K is just that constant. So K is the constant that represents whether or not we are having growth or decay. So K is the constant of proportionality. So K is the constant of proportionality, and like we set up here, it's positive for growth, or greater than 0, and it's negative for decay, or if it's less than 0. So let's use this to solve some questions. So here's a chemistry example. The rate of decay of radium is proportional, means exponential growth. So anytime you see the word proportional, we have exponential growth. Okay, so the rate of decay of radium is proportional to the amount present at any given time. If we have 60 milligrams of radium are present right now, and its half-life is 1,690 years, how much radium is going to be present 100 years from now? So we need to kind of figure out what we have going on here. So our current amount, the initial amount that we have, so our C value is 60 milligrams. That's what we're starting out with. We have a half-life, or a time to reduce by half. So our half-life, or that time to reduce half-life, which is time to reduce by half. So in this case, we have a half-life of 100. So it's time to reduce by half. We have a half-life of 100 years. So in 1,690 years, the 60 milligrams will be reduced to 30 milligrams. So, sorry, that had nothing to do with the 100 years. That's what we want to find out. So we have a half-life of 1,690 years. If we're starting with 60 milligrams of radium, in 1,690 years, we will have 30 milligrams. It will be reduced to 30 milligrams. So that actually gives us a point to work with. So we know that in 1,690 years, that's our T value, we will have 30 milligrams left. That will turn into our amount, our amount. So let's start to plug a little bit of this in. So we know that Y is equal to CEKT. So Y is equal to 60 e to the KT. So now we have a little bit more that we can fill in here because we know what's happening down the road. We're going to use this information and we're going to fill in our T and our Y values. So we know that there will be 30 milligrams left, 60 E. We know that T is 1,690, so we have 1,690 T. K. We know T. We're finding K. Okay, so what this question is asking for us to do is to figure out that K. How much is it? What's that constant of proportionality? We can't isolate K immediately, but we can isolate the exponential part by dividing both sides by 60. So we will divide both sides by 60, and that will leave us with 0.5 is equal to E raised to the power of 1,690 times k. Now we can use implicit differentiation, so take the natural logarithm of both sides to figure out what our k value will be. Okay, I've put it on a second piece of paper just to give us a little bit of room. So we have, just from the last slide at the end, we have 0.5 is equal to e raised to the power of 1,690 times k. So we are going to use what we know about implicit differentiation to take the ln of both sides. So I am going to take the ln of 0.5 is equal to the ln of e raised to the power of 1,690k. This allows us to bring this power down in front, and that's very handy. So that's going to allow us to bring that power down in front. So we end up with ln times 0.5 is equal to 1,690k times ln of e. Remember, ln of e is just equal to 1. So we can get rid of that. Ln of e is just equal to 1. We can get rid of it. So we're now left with ln of 0.5, or ln times 0.5, is equal to 1,690k. Rearrange and solve. So we are going to divide both sides by 1,690. And that leaves us with ln 0.5 over 1,690 is equal to k. Now, we can put the natural logarithm of 0.5 into our calculator. 1,690 is just a number, so we can approximate that k is equal to negative 0.00041. So we could solve for this value, but we're going to go back to our original of y equals 60 e to the kt, and we're going to sub it in there. Okay, so we know then that we're going to lean into this one. So we know that k is equal to ln of 0.5 all over 1,690. We're going to sub that into here. So y is equal to 60 times e raised to the power of ln 0.5 all over 1,690 times t. Okay, so this is a really messy exponent, but using our exponent laws, we can group e and ln 0.5 together. So I can group this together using my exponent laws, and this really just leaves us with t over 1,690, because e ln to the 0.5, that cancels each other out. This e and this ln cancel each other out. So because they're inverses, so they cancel each other out. Sorry, I keep repeating that. But anyway, so this is going to leave us now with a slightly different looking equation. Okay, so when we cancel out the e and the ln, we are left with y equals 60 times 0.5. We haven't gotten rid of that. T over 1,690. This general equation, this one right here, is useful, and it can be used anytime because that 0.5 is what's denoting the half-life. So now we're actually going to go ahead and sub our original question. For those that don't remember what the original question was, it's how much radium will be present 100 years from now. So a little bit of work to get to where we need to be. So now we are going to say that the amount left will be 60, the initial amount, times the half-life of 0.5. Our amount of time is 100 years, and the half-life is 1,690. So this is our time, This is the time of the half-life. This is the time of the half-life. And this 0.5 just means that it is half. That is the half-life. And this is our starting amount. Okay, so now it's simply a math question. So how much is left? Well, 60 times 0.5 raised to the power of 100 over 1,690 leaves us with an amount of 57.59 milligrams. So this number makes sense because 100 is only a small portion of that half-life. So we know that it's going to be cut in half in 1,690 years. We're only looking at a 100-year time frame, so it wouldn't make sense if all 60 milligrams or even 59 milligrams had disappeared and we were only left with 1 milligram if we're only talking about 100 years. Okay, here's another example, and this one is a biology example. So, in a certain culture, the rate of growth of bacteria is proportional, and remember, proportional means exponential, to the amount present. If there are 100 bacteria present initially, and the amount doubles in 12 minutes, how much time, t, will it take before there are 1 million bacteria present? So, I'd like you to pause the video, give this one a try, and see if you can figure it out. And come on back once you've done that, and we will work through the answer. Okay, so I'm assuming if you're back, you've gone ahead and tried it. So now let's go ahead and set it up. So we know that our C value is equal to 100. That's our initial amount, 100 bacteria. We know that it doubles in 12 minutes. Know that it doubles in 12 minutes. So when T equals 12, we're going to have 200 bacteria. So that gives us a point of 12 and 200. This is my T, this is my Y. We're going to use this to set up our equation to figure out what derivative we're going to use, what equation we're going to take the derivative of. So we have Y equals CE to the KT. I'm going to sub in what we know. Y equals 100 E. Our T value is 12, and we're trying to solve for K. We're trying to figure out what's that proportionality. So now we're going to use our 200. 200 is equal to 100 E to the 12K. Now I'm going to divide both sides by 100. And that leaves me with 2 is equal to E raised to 12 times K. Now we're going to go ahead and take the derivative. We're going to use ln and take the natural logarithm of both sides. So we end up with ln 2, and that just allows us to bring the power down, times ln of E 12K. We're going to bring that power down. Ln 2 is equal to 12K ln E. Ln E is equal to 1. So we're going to cross that out. So now we're going to divide, because remember, we're isolating for K. So we're going to divide by 12. So K is equal to ln of 2, or the natural logarithm of 2, all over 12. Now we're going to go ahead and we're going to put that back into our equation to use that inverse of E and the natural logarithm to cancel out and get us an equation that we can go ahead and use. Okay, so I've added another page just to give us a little extra room. So I have gone ahead and subbed in my K value of the natural logarithm of 2 over 12 into our original equation. Y equals 100 E, now raised to the power of ln of 2 over 12 times T, because it's T that we're trying to solve for. Now remember, this E and this ln are going to cancel each other out. They are inverse. So we end up with Y equals 100. Bring the 2 down, T over 12. So we know that we are aiming for 1 million bacteria. So how long will it take before there's 1 million bacteria? So now our y value is 1 million. That is equal to 100 times 2 raised to t over 12. We are going to divide both sides by 100, and you're going to see there's a method to my madness here in a second why I didn't multiply that out. And that leaves us with 10,000 is equal to 2t to the 12. We can't eliminate, we need to have it something raised to the power. So that 2 has to stay there. So we could take the ln of both sides, but I want you to take a look at my solution. I took the log because it really doesn't matter which one we do. So I just wanted to show you the difference here, or just show you that you can do both. So I'm going to take the log of both sides this time instead, and we get the log of 2t to the 12. Again, I'm going to, log rule, natural logarithm, same difference. I'm going to bring that power down. So log 10,000 is equal to t over 12 log of 2. We're going to multiply both sides by 12 to get rid of that 12 on the bottom. So we end up with 12 times log of 10,000 equals t log of 2. Going to divide out by that log 2 because remember, we want to get t by itself. We're going to divide out by log 2. So t is going to be equal to 12 log 10,000 all over log of 2. And we can go ahead and just put this in our calculator. These are all just numbers. So t, our time, will be approximately 159.45 minutes. That's how long it's going to take for these bacteria to go from 100 bacteria to 1 million. We didn't talk about this, but this 2 here means doubling time. That's what that means. So that's pretty fast. Bacteria grow pretty fast. Wash your hands and don't touch a lot of things at school. Schools are very dirty. Okay, we're going to look at one more example. So the rate of natural increase of the population of a certain city is proportional to the population. So if the population increases from 40,000 to 60,000 in 40 years, we're going to determine an equation to represent the population. When will the population reach 70,000? And we're going to determine the rate of growth after 50 years. So 3 parts to this question, but all things that we now know how to do. Again, pause the video, give this one a try, see what you can come up with, and then come on back to take a look at the answer. So let's take a look. Let's determine an equation. That's always the first step. So we know that the initial population, so this is part A. We know that the initial population is 40,000. It goes up to 60,000 in 40 years. So what's that ratio? By what factor did it grow? So if we have 60,000, we want to find the ratio, 60,000 over 40,000. Well, it's growing at a rate of 1.5. So we know then that y is equal to the initial population of 40,000 times the rate that it's changing, which is 1.5. It's growing by 1.5, and it's doing that. Every 40 years. So we have t over 40. That 40 is how long it takes. And t is going to be the time to get to our next population. So for part B, now we're going to use this equation to figure out for 70,000. So I have a feeling I'm going to need extra space, but we're going to give it a try and see how we make out here. just before we move on to part B, I do want to show you, I kind of cheated a little bit when I did it the way I did it. So I found the ratio and I immediately plugged it in. If you wanted to do it the way we had been doing it, then we could go ahead, and I'm going to show you that now. We could go ahead if we wanted to and set it up the way we were doing it before. So we would have y, and that's using the natural logarithm of each side. So y equals 40,000, the natural e, or Euler's number, raised to the kt, because remember this is c times e to the power of kt. We know that the population that we're finding is 60,000. That equals 40,000 e to the kt. We are going to, and we also know that k, we know that t is 40. So we know that that time to grow to that is 40. So we know that it's 40k. So we're just trying to isolate that k value. So I'm going to divide both sides by 40,000. We end up with 1.5, which is equal to e to the 40k. We're going to take the ln of both sides so we can bring that power down. So I'm just going to move this, scooch this over. So the ln e raised to 40t becomes 40t times ln t. Rearrange to solve. So k is equal to ln of 1.5 over 40. So we know if we plug that now back into our original equation of y equals 40,000 e raised to the power of ln 1.5 over 40 times t. Remember, the e and the ln are inverse operations. They're going to cancel each other out. So we end up with 40,000 times 1.5 raised to the power of t over 40. So we got to the same point. We just did it the calculus route rather than just getting the proportion. So however you got to that equation, that is the equation that we need for part B. Okay, so now for part B, I am going to scooch us over onto another piece of paper because I really feel like we need some more space. So we have y is equal to 40,000 times 1.5. That's how often it doubles. That's the rate raised to the power of t over 40. So now we are being asked to find out when will the population reach 70,000. So now our y value is 70,000. So 70,000 is equal to 40,000 times 1.5 t to the 40. We're going to move some things around. We're going to get rid of that 40,000 in front of here by dividing it out on both sides. That leaves us with 1.75 is equal to 1.5 raised to the power of t to the 40. Now, we're going to take the ln of both sides. Take the ln of both sides. That allows me to bring this power down. That becomes t over 40. So now I am going to divide this out and rearrange and solve. So I am going to say that t is equal to 55.2 years. So it will take 55.2 years to reach a population of 70,000 at a proportionality rate of 1.5. So the last part of this question, part C, was asking us to determine the rate of growth after 50 years. So for this rate of growth, to do that, we need to take the derivative. So what is that going to look like? Well, we have y equals 40,000 1.5 to the power of t over 40. Remember, to take the derivative of this, we're going to set this 1.5 t over 40 as being e to the power, or being a number to the power of u. So in this case, it's not e to the power of u, it's actually just a value, and we're going to just say that that's b to the power of u. And if we have something, we're going to use the power rule, so b to the u times the derivative of u times our ln b, or ln b. Okay, so let's go back in and let's take the derivative. So the derivative of this is going to be, so we've got the power rule or product rule happening. So we have 40,000 times 1.5 t to the 40 times 1 over 40 times ln of 1.5. Derivative of t is 1 over the original 40. So when t is equal to 50 years, now we can go ahead and sub in. So what will our derivative be? What will that rate be at 50 years? So that will be 40,000 times 1.5 all to the power of 50. That's our time in years, all over our time to double, times 1 over 40 times ln of 1.5. So in 50 years, the rate will be 673 people per year. Okay, go back and rewatch this if you need to see how I set these up. And go ahead and give the practice questions a try. These ones are just posted to the VLE. There's not actually textbook per se questions for this. I've pulled them from another textbook. So go ahead and give numbers, as many as you need to. Numbers 1 to 10 a try. If you have any questions, feel free to send me an email.